Okay, welcome to the second part. So as discussed in the previous video, in differential PCM, we are not going to transmit the quantized level. Rather, what we will do, if m of k is the quantized level at kth time sample, we make a prediction of this kth time sample, and then what we transmit is the difference of the actual value minus the predicted value. Okay, but there is one difficulty here. The difficulty is that we know that this prediction is made based on the previous values, right? As we have seen in that Maclaurin or Taylor series. But what we are going to transmit is actually the quantized version. So we will be having actually mq of k minus 1. This is the quantized version of mk minus 1. Suppose if you have two quantization levels, and let's say this point is mk minus 1. So you will map it to this point, midpoint, which is mq k minus 1. So there will be more error because of that. Why? Because based on quantization, quantized levels, what you can predict is not m hat of k. Rather, it is m hat q of k. It is the quantized version of the estimated value. So what is better is that instead of estimating m hat of k at this level, let's estimate m hat q of k, that is the quantized value of m hat, and then subtract that from m of k. What we will get is the difference. We will transmit this difference signal instead of transmitting m minus m hat. Now let's see how the system will look like. So see, we have the input like this. So we have m of k coming at the kth point. Then we need to generate the difference signal d of k. So for that, what we will do, we will feed in here m hat q of k. See, this is the estimated value or the predicted value of quantized sample, quantized kth sample, and the difference is the d of k. Then this d of k will be quantized so that we can transmit it. So we pass it through quantizer. Okay. So what will be the output will be represented by dq of k, and this is given to the channel. Okay. So now we have the feedback system. You see, what we will do is we will take this as input to prediction filter. We call this predictor. So what will this predictor do? So this predictor will basically generate the quantized prediction of the message signal and q hat of k. But what should be the input to the predictor? See, as per the equation, input should be mq of k. Okay. So but if you see here, it is dq of k. So we need some modification. What we will do is we will put a adder here also. Okay. And how to get mq of k? We will take one input connection from this in this direction. You see, we are now supplying here m hat q of k. Now let's look at the equations. So one equation is the main equation where you first predict the quantized value of message signal at time sample k, subtract it from the actual value which you will receive afterwards, and this is the difference which we are going to now after this you quantize. You have this dq of k. You are basically quantizing the difference signal also. So when you quantize the difference signal, what will be this equal to? This will be equal to d of k plus, we have already done this quantization noise. There will be some quantization noise which we represent by q of k. Now look at this. What is done here? So you have basically an adder here. You are giving the input dq of k. You are giving the input m hat q of k. So what will you get? dq of k plus m hat q of k. This is equal to d of k plus some quantization noise plus m hat q of k. From this equation, what is m hat q of k equal to? So you see it is d of k plus q of k. M hat q of k is equal to plus m of k minus d of k. So it gets cancelled up. So this becomes m of k plus q of k. What is m of k plus q of k? It is message signal corrupted with quantization noise, which is exactly m q of k. So this is mathematically why we have adder here. What it does, I repeat, it takes the input as this difference signal, which is the output to channel, as a feedback point. Then what it does is there is a predicted value of this message signal m hat of qk, which is fed back here as input. So it gets added up. So we add them up and use this equation. What we get is the predictor output is m hat of q k, and this input here becomes mq of k. Now what will the receiver do? See, what is the input to receiver? The input to receiver is the quantized value of the difference, right? So this is fed to an adder, right? So what should be the output of this adder? Of course, the output we want is the quantized version of message signal. So how will we get this output? Basically, we need again a feedback system. So we again will feed this output to the predictor filter. Okay, and what will be the output of predictor filter? So the output of predictor filter will be m hat q of k, as we have seen previously also. This you add here. So you can in fact verify also, because dq of k, we have shown it. You see here dq of k is d of k plus q of k, and d of k is m of k minus m hat q of k plus q of k. Okay, in fact you can write this as m of k plus q of k minus m hat q of k. mk plus qk is the message signal value plus quantization noise, which is mq of k minus m hat q of k. You see, this is dq of k. Now what we are doing here, we have here dq of k. I will again write here m of k, mq of k minus m hat q of k. Now at this point you are basically adding what? So you are providing this mq of k as the input to the predictor, and the predictor output is m hat q. So that m hat q gets added, m hat q gets added to the difference quantizer signal, and that mathematically becomes mqk minus m hat qk plus m hat qk. Okay, so it gets cancelled up, so we get mqk as the output here. That is how it works. Now coming to delta modulation. Delta modulation, you can see the special case of differential PCM which we have seen. What we first do in delta modulation is we sample at very high rate. So sample at very high frequency, sampling frequency, typically 4 times 90. So what is the result of that? So let me show graphically. Suppose this is the signal. Let's say in DPCM you are doing this much sampling. Fine. So what you have, let's say that this is m of k. Okay, and so this is m of k plus 1. Okay, and then you have the quantization levels also. So what you will basically be doing is you have quantized version of m of k, and you are making prediction about that. Let's say you are making a very simple we will use very basic prediction that if you are at sample k, then you want to make its prediction, so it is m of k minus 1. Okay, so even if you take the quantized version, so this is the difference, and let's say this is your d of k. Now if you sample at this frequency, so what will be the d of k? So d of k is just the difference between the two levels. So let's take these two. So this is like this, and this is suppose m of k, this is m of k plus 1, right? So what is the difference? Difference is this much. Okay, so you will use some number of bits to represent this d of k. Now if you increase the sampling by 4 times, so see, I will draw now more sampling lines here. So now the two consecutive samples will look like this. So you increase the sampling level such that you just need 2 levels, that is 1 bit for quantization, and that is quite possible because when you choose high next frequency, high sampling rate, sorry, then the consecutive samples will have very less difference. Okay, so this is the basic idea behind delta modulation, and you can basically say that delta modulation is just 1 bit differential PCM. So now how to achieve this, I will directly go to the block diagram which will explain it. So here is what you have this m of k, okay, message sampled at kth time, then you have an adder, then what you expect the output of adder to be is actually the difference. So how do you get difference here? You need to feed back the quantized version of the estimate, and in delta modulation the estimate is just the previous sample, so mq of k minus 1, quantized version of previous sample. So how to generate that, we'll see. Then you will quantize this difference. Okay, so typically this will be 1 bit quantizer, simple 1 bit, and then you get here dq of k. So how to generate this mq of k minus 1? We basically take again the feedback signal here. Okay, so we will have again an adder here. We'll see why. So that the output here is mq of k, and this mq of k is fed to the delay element. So here is delay element. So now the predictor here is simply delay element, because what you need here is you need mq of k minus 1. See, when you feed the mq of k, you will get mq of k minus 1. But how to get mq of k here? The input is dq of k. So we'll take this point and feed it to this adder with plus and plus here, and here it is plus and minus. That is the analysis. It's very simple. First of all, at this point you see d of k is m of k minus mq of k minus 1 as expected. Now after quantization you have dq of k. So we know that dq of k is mq of k minus mq of k minus 1. Fine. Now this is fed to this adder, right? So what are basically we adding here? So we are adding mq of k minus 1 plus dq of k. So very simple. So when you add them up, what you get is you get mq of k. mq of k is applied to delay element. The job of delay element is to introduce one time delay, so you will get mq of k minus 1 as the output, which is then fed back to the input as well as this adder, and this is how iteratively it will generate the difference quantizer signal. Now what about delta modulator receiver? Pretty much simple and same as DPCM, but the only thing is instead of predictor you have a delay element. So you have dq of k, this is what receiver will receive, the quantized difference signal. So fine. So this will be fed to an adder, and what you expect at the output is mq of k, the quantized version of the message signal, right? So how to get this? We will be actually taking feedback. Again, this is a single delay element with time ts, sampling time, and here what we get as the output is mq of k minus 1. This is fed back to this is plus, and this is also plus. You see, now mathematically we know that dq of k is equal to mq of k minus mq of k minus 1 and when this is fed back and added to it, we get it gets added up and cancel, and we get mq of k at the output. So this much for the delta modulation. I may also be submitting one video on numerical, so that you will be more comfortable with solving the numericals. So I may make a separate video or hand out notes for that. Thank you.